At the very beginning of the course, I explained about the physician's health study, right? And we talked about testing and the experiment that was conducted with male physicians on the effectiveness of aspirin in reducing the risk of heart attack. And we compared, or I explained how they compared on they compared the results of the group that was known as the treatment group who actually received the aspirin with a control group that did not receive the aspirin. And I made some very general statements about comparing the results of death, and the ones with the group with the lower number of deaths by heart attack was the aspirin group. And then with that, they came to the conclusion that there's significant evidence to suggest that taking aspirin reduces the risk of heart attack. Okay, so how did they do that? Again, how did they decide that that was different enough? Like, we can look at numbers and say this is different from that. Now, this is not the same as when you're talking about like an election and voting. And in an election, you look for 51%. The one who gets 51% of the vote from two candidates, if you're comparing two candidates, the one who has 51% wins, right? So one is enough to say there's a difference. But in statistics, that's not necessarily the case. To be significantly different, we have to decide, given the variation in the data or the sample that reflects the population, given that variation, we get an idea of what is strange or new or something worth calling different. Okay, so that comes full circle to the end of this, and this is the last thing I talk about, where we have two populations here of results. They try a fertilizer on a plot where tomato plants are growing, and they're being grown with the old fertilizer, and then another plot that's comparable. Remember, we talked about matched pairs design, so it's a comparable plot. So there's an attempt to take control over the environmental conditions, and the watering conditions and the air quality and all that. And then the only thing that's different, they attempt to make the only thing that's different is that it's a different fertilizer. And they take a sample of 4, which is not a high sample, but I don't want to give you too many numbers because then it becomes a problem of entering numbers as opposed to a problem or an exercise in statistics. So what we have to do there, because I have matched, so this plant yield 2.2 pounds of tomatoes were grown on the plant over here, but over here, these are matched. So it means that the plot for this plant was similar in every other way, except for the fertilizer, to the plot for this plant. And so they are considered uh like matched, or they're dependent. We call it dependent. There's a relationship between them other than the fertilizer. And we take the difference and we do all that. When we do that, we eliminate the need for this two samples, and we convert into one sample. And now we proceed with the regular t-test to look to see what do we want to see here? What test do we want to conduct on this difference data? If there's a difference, then on average, this number should be different from 0. It looks like it's different from 0, but in statistical terms, is it significant? Okay, so that's the difference in statistics, is that we have a whole science built around, or theory, if you want to call it. I think that's maybe a better way to refer to it at this point. Theory built up that we can talk about what's different, what's bizarre, what's new, what's special about some result that we find. So that's what we're going to do. We're going to see if this on average is different from 0. And that's the test that we run. This little d here just stands for difference. You don't have to put that on your paper when you write your exam, but I'm putting to differentiate between what we were doing before and here. Basically, that we had to collapse the data into one data set and look to see if the average is different from zero. And that's what we're going to do. And in this case, we're checking for an improvement or a positive effect on the yield. So we're looking for a higher yield. So we're going to check against the alternative that the difference is more than zero. But if we were just looking for a difference, we would just check it against it not being equal to zero. If we're looking to see if if a fertilizer worsens the yield, then we would look for an alternative that is less than zero. Okay, so that is how we go about this. And this is the last thing I teach. Now, what if there is no relationship between the two? Like here, they were on the same plot or similar enough plots that I called them a matched pair and difference their result. But if there is no relationship like that between two sets of data, then you have to do what's called a test for a difference of two independent samples. And that's what this is all about. And I leave it here, but I don't test you on it because I want you to be really good at the basic stuff. And this is going to be easy after. Basically, this is for okay, so we start with two proportions, but then you can also do it for two means. And then there's different conditions and different ways to do it. This looks similar here. Okay, so let me step through it. So here you have the hypothesis test that the difference is equal to 0.03. This is about what? This is about respondents to the question of the students have a cell phone. Okay, so you find out between the years 2003, 2004, and you ask different students. That's the point. If I ask the same student from 2003 to 2004, then it's not like this. They would be dependent because it's the same student, just like the same plot of land. To plot my different my tomato plants with different fertilizer. In this case, and mind you, if I'm using a fertilizer and I'm using the same plot, it should be that they're divided, right? That the fertilizers don't mix or anything. It's basically in every other respect, those plots are identical. And any kind of variation from that or any kind of limitations that you have in your study, you would write it up in your study if you think that you weren't able to control all those variables. But let's say we took 2003, 2004, and we just walked around and asked students on a campus if they have a cell phone. They're different students, right? It's not necessarily the same student. So that we would call those samples independent, and then to compare to see if the difference between the proportion of students that have a cell phone is 3%, this is how I set it up. And otherwise, it's the same theory. I'm going to standardize the point estimate that I use. What's the point estimate I use? I'm just going to get the proportion from each sample and subtract them. And I said I want to check if the difference is different from 3%. So is it going to be more than 3% or less than 3? Did it go down? It's never going to go down. But anyway, and then this is my standard error. That looks familiar, right? This looks familiar. What does it look like to you? What is this just by itself? Do you remember this? So this looks like at the end of the course, it looks like the standard deviation, right? It looks like the standard deviation. The standard deviation, the estimate of the standard deviation is what it looks like. But I have, I'm going to find, it's over here. No, I opened it up. Anticlimactic, where did I put it? All right, here. Okay, but it's the standard deviation from the first sample, and this is the standard deviation from the second sample, and I'm adding them and taking the square root. Why is it that I add them? Does anybody know or remember? So all this is based on the theory you know. So when can I, to get the standard deviation of, basically I'm getting the standard deviation of P1 minus P2. I use my rules of means and variances, and remember that if the two variables are independent, I just add their standard deviations, their variances together. Right? So this is the variance of the first one plus the variance of the second one. And then I take the square root to get back to the standard deviation, which I call the standard error. So this, I'm never going to test you on this, but I want you to be able to read something like this and not feel like, oh, where the heck did they get that from? Well, that's using the rules from module 7, 6 and 7, I guess. And the rules from inference module 9. The whole idea of doing the test, in other words. But this itself, getting the standard error of this difference, we basically, if they're independent, that's what we assume. So we have two populations. They are not dependent. In other words, they're independent. So I can add their variances and then take the square root, and that's just fine. So, and then you just carry it out. So, basically, this shouldn't be too foreign for you. This is a little bit of a, this is about two means, same idea. And because when we use T, it's because we don't have prior knowledge of that variable, right? So we have to use the T distribution. We don't know about the standard deviation or how variable or how spread out the values of the distribution are. So we just go to the T distribution. And so this should look familiar as well. This is the variance of the first population or the sample, and this is the variance of the second sample, and we assume independence. So it's the same idea. But what's going on here is there's all this stuff here. So this is for if there's this in general, this is the standard error. This is a little more fancy, and don't worry about it, but it's just a modification that statisticians made as an alternative just to double check, basically. Oh no, this is the different, sorry, this is the degrees of freedom. No, this is the calculation of degrees of freedom. And yeah, so these are some results that look, they stray away from the simple things that we're doing, but you can appreciate that someone figured out that this was a better thing to do, okay? I'm not going to get into the details of any of this because I think to do this, you should be in a higher level statistics just so you take time to discuss like all these kind of different results, but they're used in the same way, okay? So I put it in here for people who've taken statistics before and they want to see how it links to other things they've taken. It's just a summary. And the last thing I have here is regarding chi-square test, and that's very interesting, chi-square test. It's to test, and you see this a lot, you know, in the news, or if you read research, you want to know that if, for instance, this variable, gender, varies for some behavior. So are men and women different, in this case, in their frequency to binge drink? So this is drink too much, right? And so we have some data, and how are we going to see if these are different? Is this different? Is 1,392 men saying yes, different from 1,748 women? So does it mean women are more likely to binge drink? Well, it all depends because they only asked 5,000 men. Usually women are more likely to answer surveys, are more agreeable to answer questions. Men are less than women. So that's for sure. But so I can't directly compare this number with this number because we asked less men. So doing what's called a chi-square test is a way, it's a very simple, non-parametric approach that I really like that compares all these numbers and tells you if in fact it is true. So you may or may not have come across this, but it's very handy and I really like it. And you can easily get a chi-square test result out of software. So I'm not going to study it right now, but if you ever want to do it in the future and you don't know where to start, you can let me know and I'll help you. You can do it easily in Excel. Otherwise, these are the steps to calculating it, and I'm not going to get into that. And that's it. That's all I talk about. So that is the course. Then I just have some exercises that were from other courses, I mean, related courses that I've taught before. So that's all that is. And I'm not going to test you on it, but I just hope your mind is open to reading statistics, challenging things that you read, and hopefully you have time to take more courses in statistics. I don't think that's anyone in the program or if you have electives, but it's very important to have statistical literacy. I don't know, I've never heard the term. I think it's really important. And I'm going to emphasize that in our reality, that's what you hear about a lot. People throw statistics around. And it's really important to know where they came from and how to properly evaluate. So in terms of the notes, finish the notes, all I do is I lean heavily on the formula sheet and teach you about all the elements of the formula sheet. Last time we met, we talked about 1, 2, and 3, and we left off at 4. And what we have here in the first column is calculating an estimate of a parameter with a sample and no other knowledge. We create a confidence interval. The next column is regarding how you, what's the appropriate sample size to get a particular level of precision. And the last column is for hypothesis testing. Okay. So it's all should be there in the videos. If there's something that is missing, you guys can let me know. I think it's all in there. And where I want to start today is looking at the homework, which is here, and say a couple of things. Okay, tell me honestly. Okay, well, no one, I already asked you, right? Who started the homework and or finished the homework? I wasn't sure my question, but I'm going to start here. So we're going to read this problem, and you're going to tell me which of the formulas, row 4, 5, or 6, we should refer to in solving this problem. A gas utility company wishes to know how much time is needed for the service person to handle a service call. A random sample of 16 gave an average time of 62.2 minutes with a standard deviation of 5 minutes. The 95% confidence interval for the mean service call time is, all right, so what are we going to use to solve that problem? 4, row 4, 5, or 6? And which part of row 5, 4, 5, or 6? Nobody else? Okay, let me I'll put up the question. All right, so the students that we can count on who are up to date have chosen 6. All right, so why is it 6? So let's hear from somebody who didn't know the answer and tell me what you're thinking about when you read this question. You can write in the chat or you can speak up. You know it's about confidence interval, which is the first column. So you know it's going to be either this one, or this one that you're going to use to solve the problem. So the first issue is the question about proportions or is it about an average? What is the question about? So that's the first thing that you have to look for. I mean, if you want to do this in a systematic way. So they want to know about the average time, okay? Average, very good. Average time. So that's the key word there. So that tells you that it's either 5 or 6 because it's about the average, inference on the mean. Now, which one is it, 5 or 6? So what we have to do is the second thing is now that we know it's the mean, we have to read, do they give you the standard deviation or don't they give you the standard deviation? So that's what you read next. So what's here? It's here. Do they give me the standard deviation? Who says they give me the standard deviation? Put it in the chat. Do they give me the population standard deviation? Yes or no? Do they give me the population standard deviation? The population standard deviation. The population standard deviation. The answer is no. They don't give me the population standard deviation. What did they give me? They gave me the results of the sample. They gave me the sample results. So this one is X bar, and this one is S, not mu, not the population standard deviation. Sorry, not sigma, the population standard deviation. They gave me S. All right. That is why we have to use 6. All right. So those are the 2 things you have to do when you read these problems. First, you look for, is it about the mean or is it about the proportion? And most of the time, the questions are about the mean. All right. I spend a lot of time with 8, module 8, and module 8, we work with the proportion a lot. And then so I begin module 9 talking about the proportion, and it's very useful and very important, but in practice, you're going to work a lot with averages. Often it's with the average that you work with, so I end up spending a considerable time. Not that you should forget about proportions, but you need to distinguish between them is the most important thing. And this inference document, this homework document is mostly about averages, but that doesn't diminish the significance of working with proportions. So step 1, read, is it about a proportion or is it about a mean? And this one's about a mean. Second, since it's about the mean, is it about, do we know that sigma is given? Or are we given nothing about sigma and we have to use S from the sample? So in this problem, we don't have sigma. We have the results of a sample. How do I know? Because it says a random sample. That's how I know it's the sample standard deviation. All right, write that down. Write that down. So we're not going to solve it because it's easy to plug in numbers, I think. But let's look at the next one. Oh, no, let's not look at the next one. Let's go to number 4. All right, so tell me which formula I'm going to use here, 4, 5, or 6? Which set of formulas do I refer to, 4, 5, or 6? A can reprints 16 ounces on the label of one of its products. The quality control supervisor selects 9 cans at random and weighs them. They find that the average weight of the 9 cans is 15.7 ounces and the standard deviation of the 9 cans is 0.5. An 80% confidence interval. Okay, so is this about the mean or about the proportion? Okay. You guys see it's about the mean. The mean or average weight. Do you see that? Now, probably 85% of the time this strategy works just to do this, but you have to don't get tricked because sometimes they're going to use slightly different words and you might get confused. But this you're guaranteed to get a B, 85%, if you just follow these steps. Okay, so mean. And the second question is, do I use formula 5 or 6? Do I know do I know the population standard deviation or not? Do I know it? Do I know the population standard deviation? Is the population standard deviation given? There is a standard deviation, but read it again. It says of the 9 cans, this is the sample. It's not the population. So that information is about the sample. That's S. So you have to use number 6. You don't have any information on the population standard deviation. Okay, I have one more key question. Let's say you had a problem and the problem gave you both the population standard deviation and the sample standard deviation. Which one do you use? If a problem gave you both the sample standard deviation and the population standard deviation, which one do I use? Do I use S or do I use sigma? In other words, which one is better? 5 or 6? Better in terms of accuracy. You guys, I could always trick you, right? It's not a trick, but I know where there's the missing understanding. The answer is 5 is always better. 5 is better because you actually have the real population standard deviation. It's going to be better. But 6 is the second best option. 6 is the second best option, right? It's at least an option. And 6 is more popular because usually you don't have that special information. Yeah, you usually don't have that special information about something like the population standard deviation. All right, so write that down. You should use 5. 5 is better because you're using the actual real population standard deviation. Okay. So those are the main things I want to say to you. Let's do a couple more. Let's see if I can. So I'm not solving them. Again, solving them, once you figure out which one to use, you just plug in the numbers, right? And which we can do a few of those. All right, let's see. All right, so which formula do I use here? 4, 5, or 6? It is desired to estimate the mean dining room and bar tab for parties of 4 which dine at a particular restaurant. The resulting confidence interval should have a width of 10 and a confidence coefficient of 95%. A reasonable value for sigma is $25. What is the required sample size? No. Do I use 4, 5, or 6? Okay, first question. Is it about the mean or about the proportion? Mm. Okay, so you guys see that. The estimate, the mean dining room and bar tab for parties of 4. Good. So it's about the mean. So it's either 5 or 6. So which of them, 5 or 6, do I use? And the question is, do I have sigma? Sigma is given. So we use 5. Good. We have sigma. All right. So then you just plug everything in to get this sample size. So this is the sample size estimation. I said we'll do a couple of problems in there, or problem. Why is this missing here? Why don't I have sample size estimation for 6? Now, I do believe I discussed it in the videos. Why is there a big blank there? Nobody knows? It is not the same formula as 5 because I don't have sigma. So 6 is all about sigma unknown. Okay, so you guys have to watch completely the videos. Don't go into other internet or wherever you're going. Don't go anywhere else. Just watch my stuff and ask me if you have a question. Because it's all there. Okay, so you can't just use the same formula because we don't know. So 6 is all about not knowing sigma. Um, so here, this is inference on the population mean, sigma known. But if you don't know it, if you're not giving it, you don't have any data you can say, oh, it's just the same as this old data. The best thing to do is use S instead of sigma. So you see it's the same formula, except I'm using S because sigma is not known. But when I do that, the cost of doing that is I can no longer use Z. I have to use this thing, a new distribution called the T distribution. And so basically it's putting S in here and T instead of Z. Let's say I did that here. Let's say I just did that. I said, well, I don't have sigma. I'm just going to use S. And M is the margin of error. And like that. So what's wrong with doing that? Why can't I use that? So this is supposed to solve for the sample size. And it solves by We solve it by taking this expression and calling it m. This is called the margin of error. And then I do algebra to isolate n, and that's where this comes from. And I know I show that in the video. So why can't I just do that here? What's the problem with doing this? Why is this wrong? Well, what is S? S is equal to the square root of the average square deviation from the mean. And what do you see inside of S? Another n. So if you use S here, you're not really isolating n because n is still in this equation. Okay? So you can't isolate n out of here. Well, let me think. If I square that, oh, and then also n is here. Right? To get x bar, I also have an n in here, and I would have to get that out too. So I have to get that out and that out. Like the algebra is messy. I think it has no analytical solution that's clear. So this is not going to put n on the left side. We have an isolated n. You could use this, like a computer software would be able to estimate this by iterating and trying to balance the equations, taking different results, getting different X bars. I don't know. It would be an estimation exercise. But this one uses the true sigma. This one up here, when we do the sample size estimation, use some known p value, but it's not the case here. The result is depending on a sample, which is antithetical to what we're trying to do here, right? We're trying to find the sample size before we take a sample. So here it's counting on having a sample to do it. So anyway, this is not done. Okay, so that's why it's not there. Any questions about what I'm saying here? Okay, so in summary, first step, question 1, you check out if it's the mean or mean or proportion problem. If it's a proportion, you just go to row 4, right? If the question is about the mean, all right, let me do it like this. If it's about the mean, the second question is sigma given? If it is, you go to 6. If no, you go to 5. Okay. Sorry, I did it backwards. If yes, you go to 5. If no, you go to 6. Okay. I don't know why I did that backwards. And if both are given, all right, that's what I said in summary. Okay, so we spent an hour in my review. Let us do some problems together. Okay, let's look here. You guys can take a screenshot. Still there for a second. Is this helpful so far? I feel like it is because you guys are saying some of the wrong things. So I'm correcting you. Uh let's see. And I know there's still some people who need to catch up, but hopefully this is not wasting your time. I don't think it is. I think it's putting you in the right direction. All right, here I'm gonna project and you can do the same analysis I just talked about with this problem. And say problem 22. And question number 1, is this about the mean or a proportion? Mean, very good. Okay, so it's about the mean. And the next question is, now that it's about the mean, do we have the standard deviation of the population or no? Yes, you see how it is? It's right there. All right, so which one do we use? Which formula do we use? Four, five, or six? Okay, you're right. It's about 5. Now, it's about 5. It's about 5, and you want to get the p-value. You're going to use 5. Okay. So, should I give you some time? I'm going to give you, let's take a break. Let's take 10 minutes. We'll come back at 10:10. You guys try this problem. Okay, I'm back. How'd it go? Did you finish? Need more time? Carla finished. Okay, put your answers in the chat if you finish. Jordan, the details. Okay. Okay. Um, okay, so there is evidence that the true mean amount spent on textbooks by U of M students in one semester is greater than $400. That's what we want to test. So there's no other information here. The first step is to set up the hypothesis. And you have to always, for the mean, this is always the setup I explain in the videos. And you just have to figure out what number goes here. And what sign are you going to use? Not equals, greater than, or less than. So what number I'm going to put here? What am I testing? I want to look for evidence that the true mean amount is greater than $400. So I do know that I have to put greater than $400 here. Never do you put any other sign than equals in the null hypothesis. And this is a statement of the status quo. This is what we believe to be true when we're doing our test, given prior information. I'm going to put the number 400 in here. But we're going to see our test is to verify if there's evidence that it's greater than 400. Okay, so in the black is always the same. You're going to always put an equal sign there. So that rules out putting the greater sign there. So don't mess that up. Okay, so that is the first step. That's what I want to test. The second step is going to be A for assume. What do we assume? To proceed with this problem, we assume the null hypothesis is true. So we're going to assume that this is the null hypothesis. I put a little 0 there. Null for no or not. So they put a little 0 to denote that. And this is what we will believe to be true. And then we're going to look to see if we have evidence against that assumption. It's $400. Because it's $400, then we know if we had a sample, it doesn't tell us. It doesn't tell us about the distribution of X, the number, like how much they spend. So X means in this dollars spent on textbooks. And X is, we can either assume it to be normally distributed, or we can just say X has a mean of 400. Well, let me write it. And they tell you it has a standard deviation of 165. They don't tell you the distribution of X. Okay, but that's okay because we got a sample of 50, which is greater than 25, which allows us to use the central limit theorem. That says if you take a sample, that result comes from a distribution that's approximately normal with a mean that's the same as you had originally, but a standard deviation that's smaller. The standard deviation of the sample mean distribution is going to be the original sigma divided by square root of n. So what will that be? That will be 400 divided by square root of 50. No, sorry, I put 400. 165. I don't know. Sorry. And you get, you can round it to 2 decimal places. Okay, so it's also dollars. $23.33. Okay, so now the next step, so these are the steps of HAPC that I explained, is to assess the evidence. A for assess the evidence. What's the evidence? The evidence from the sample that they took of size 50, the mean was 430. Okay, tell me about 430. Is 430 like 400 or is it more than 400? Is 430 same as 400 or more than 400? Because that's what we're saying, right? We assume that it's 400, but then we get a sample result that's 430. So do you think that's the 400 or more than 400? Okay. So you think it's do you think 430 is the same as 400 or more than 400? So this is the practice of statistics. We're going to figure out if the standard deviation is pretty big, 165. So that's allowing within one standard deviation, plus or minus 400. All the numbers around that are considered to be similar for the original population, but for the sample, you have 23 as a standard deviation. So one standard deviation is like give or take 400. So that's not strange. Two standard deviation is give or take 40. So this kind of falls within two standard deviations of the mean. So could it be just 400? So we're going to be more specific. We're going to put this together in a standardized way that we know. I don't know why only Carla answered my question, but hopefully you're interested in knowing, is this different? So we need to assess it. We're going to assess this and by converting it into the number of standard deviations X bar is from the hypothesized mean. So we're going to use the hypothesized mean, and we're going to use the standard deviation of the sample, this new thing here. So we're going to use this over here. And we're going to use the assumption, this over here, and standardize X bar and see how many standard deviations it is away to see if it's the same or different. So we put 430 first, and we minus the mean hypothesized, which is 400, and we divide by 23.33. And what do we get? I'm going slowly so you have time to work on it. Are you guys working on it? If you guys aren't working on it, I'll just go faster.
What will you live on after 60?
Okay, 1, 2, 8, 5. 8, 9. Okay, so we're going to round that because it's a Z and we're going to use our table. Usually it's going to be 1.29. All right, what do we do with this number? So this is where we get to the p-value. They don't even ask for the, they don't ask for even the result. They just want us to get the p-value. So what I'm going to do, first of all, is discuss this. What is 1.29? 1.29 means that the result 430 is 1.29 standard deviations from the mean. Is that considered unusual? Is the question. What is unusual is the sub question or the question before that. What we're going to consider as unusual is if the chance of seeing it was so small that we saw it. Okay, so we got to figure out what small is, and we say that if the chance was less than 5%, that's usually our rule. If the chance was less than 5% of seeing it and we saw it, then it's bizarre. So how we're going to check about the percentage is calculate the p-value. The p-value is the probability of seeing a Z statistic, because this is a statistic. Remember what a statistic is from the first class. It's a number calculated from a sample. Well, here's a sample, and I do all these things to it. So Z is a statistic. This is Z statistics. So the probability of seeing a Z statistic as extreme or more extreme given H not true. All right, what does that mean? It means that you're going to look back to the null hypothesis or the alternative hypothesis, sorry, to talk about extreme. I'm going to check what's the chance of seeing a value 1.29 or higher, because I'm going to check what's the chance of seeing 129 or higher And I'm going to check what's the probability that Z is greater than 1.29 because I've standardized everything. So what's the chance of seeing a value of Z greater than 1.29? The chance of that you're going to get from either you can look at the left side of the negative of that off of the table, right? If you change the sign and direction, it's the same result using the symmetric standard normal distribution. So you can go into the tables and look for negative 1.29. And it's all the way here, right? Negative 1.29 is 0.0985. Very good. Oops. Guys got it. So that is equal to 0.0985. So it means that the chance of seeing that was like 1.29 standard deviations away was about 10%. So is 10% and is that like so unusual? Like is 10% small enough? So we set a standard. Yeah, I'm not supposed to do this, but basically we're finished the problem. But just to finish to answer in theory, you know, what you would do next, the answer is A. But to finish the problem itself, regardless of the question, you need to take that 10% and say, well, but is that unusual? Is that we saw this result, we got 430, and the chance of seeing it was 10%. So is that weird that it only had a 10% chance and we saw it? Well, we set the standard that says that if the p-value is less than or equal to 5% is what we usually use, we're able to say it was strange, so we can reject our null hypothesis that and suggest that something new has happened, that we have some evidence that it isn't 400, that it's actually greater. That is our rule that we usually use, and this is called the 5% that we set. Sometimes I change it, and in practice you might want to change it to make it more strict. This is called the level of significance. And usually we use the symbol alpha for that. So unless the problem says otherwise, you use 5%. In our problem, our p-value 0.0985 is not less than 5%. So we actually failed to reject. We failed to reject H naught, and we have no evidence to suggest that it's higher. So 430 is in fact the same as 400. I mean, I'm oversimplifying things, but in statistical terms, having a result of 430 with this kind of distribution is not unusual. Okay, so we don't reject the null hypothesis. There is insufficient evidence to reject the result is not significant. These are different ways to say the same thing. All right, so you guys did well. All right, so we did a problem looking at the mean, right-tailed problem, looking above, and we knew sigma. Okay, now you need to know how to deal with when you're given sigma and when you're not, and when you're giving both, you always use the sigma approach. So let's see, I'm going to find another problem for you to do. Still have an hour. I can do a few more. I'm not going to tell you what it is. You're going to tell me what is the approach. Okay, you ready for me to change the page? If not, you have the video to check back. That's just interpreting a result. Okay, try this one. Well, somebody asked me to look at the homework questions. I wonder if those were outside of the topic though, because there's a few ones in the homework that deal with independent samples. Anyway, I'll look at that after this one. It's 41, 46. Okay, I read the problem. You can take a screenshot. And let's go through the questions. Is this about means or proportions? Means or proportions? Okay, so it's about the mean. This is where you find the true mean. So your test, it's a test about mu, true mean. And the question is, do you have the population standard deviation? Sigma is not known. Okay, so we have to use number 5 again. All right. Do number 5 because this is a different test. Let's set up the null hypothesis and then I'll let you try. So the first step, right, is the null hypothesis. You have to always do it like this. It's about the mean and equals. So whatever number I put here, I also put below, and then I just have to figure greater than or not equals. So what number do I put in there? What number do I put in the box? A lot of numbers floating around. That's right, 150. It tells you to test 150. I'm going to use red. And 150. And what is the sign that I put here? Greater, less, or not equals? Not equals because it says differ. It doesn't say it's bigger or smaller. It says it's different. Okay, so the same process this is the exact same process we just did, but what is different? Which part is different? So I put unknown. Sorry, unknown. This is 6, not 5. You guys didn't stop me. Sorry. Number 6. So it's how is this different from what we just did in the last problem with number 5? Which steps change? So we did the H step. Now we're going to, what I do here is do the 2 together, assume and assess. We are going to assume that mu is equal to the mu naught is equal to 150. And then given the theory, I know that if I standardize the evidence, what is the evidence? The evidence is over here. The sample result is the evidence. So the mean was 162. I'm going to subtract the hypothesized mean. I'm going to standardize this with the information, but I'm going to use the hypothesized mean, and I'm going to use the a standard deviation, but I don't have the true one, so I have to use S instead. And this is going to end up being S over square root of n, because just like for when I have sigma, it's sigma over root n from the rules of means and variances that we learned. Instead of having sigma, I have to use S over root n. So this is the formula I have to create the statistic. The test statistic is now T. So the test statistic is not Z, it's T. Why is it T? Because we don't have sigma. So so our X bar is what? Adriana did it. Good. 162 is given, minus the hypothesized mean, which is 150. And then S is given as well as 35 divided by square root of 50. Now, just be careful entering that into your calculator. Make sure if you subtract these that you say equals first before you divide by this amount. I don't know how you do it, but I'll show you what I do. So 162 minus 150, and I say equals before I divide 35, and then I actually multiply by the square root of 50. All right, so why did I do that? So I say 162 minus 150, and then when you divide a fraction, you multiply by the reciprocal, which is actually like that. Or you can do it in 2 parts, one divided by the other. So what I just showed you was actually I did it like 162 minus 150, and I said divide by 32, and then I multiply it by 50. That's all the same thing. So make sure you can get my answer, 2.424. I'll keep one more decimal because I have to go on the T table and look this up. Which T table row do I use? I have to go to the row with n minus 1 degrees of freedom. Did I do it wrong? I'm going to double check. 162 minus 150 equals divided by 35 times 50 square root 2.42. Okay, why do I have a different answer than you ladies? I could have done it wrong. 162 minus 150 equals divided by 35. Oh, I changed the number here. That's what I see I did. I wrote 35, 32 for some reason. This is 35. Wow, it's so funny. I think it's this 2 that's throwing me off. Here, do it again. So maybe you are right. Let's double check. One 162 minus 150 equals divided by 35 times 50 square root equals, oh, get the same answer. Square root of 30. Oh, maybe. I mix up the problems when I do so many. Sorry. Let's see. It was at 50 in the last one, and this one is sample size 30. Okay, so obviously it's me. Okay, so let's clear that. 30, 30, 30. Sorry about that. Okay. And now we can get the same answer. Hmm. 162 minus 150 equals times 30 square root divided by 35. Let's see. There we go. Now I have your answer. 1878. Good. It's the zooming. I guess I zoom out and then I don't see the numbers anymore. And I remember the wrong number. So this is 1878. Okay, now what? Okay, and you can also put it in Excel if you don't know how to put it in your calculator. You put it in Excel. So it's 1.878. And we need to know the degrees of freedom because that matters to picking the correct row on the T table. So we're going to go to the T table at the end. And I explain, oh, it's not here. It's on the other thing. And I explain how to use the T table in the videos. If I don't, let me know. So what I do here is I pick this has several T tables critical values on it, but I just want the one with 29 degrees of freedom. So I go to this row here. And what I'm going to do is I'm going to drag them up. See if that wasn't even a good cut. Okay, do it again. Okay, so this is the 29th row. Can you guys see that? So I'm looking on the 29th row. How is it possible that this is off? There. So I drag the 29th row up here. Just do not see it. Okay, so I'm looking on this, and this is giving me the distribution for 29 degrees of freedom, which is 30 minus 1, because 30 was the n. To get degrees of freedom, I take n minus 1. And this gives me the critical values on the t distribution. So this is basically the shape with 0 in the middle. And it gives me the right side. And I want to find the right tail probability corresponding. So if you are at 0.683, there's 25% on the right side. If you're at 0.854, so as I move this way, it goes smaller and smaller because the area to the right diminishes. So these are the critical values, the values on the bottom here. And these are the right tail probabilities. So the value that we had was 1.878, and that is not exactly on here, but it fits between these two. If you want the exact value, you can go into Excel to get the exact value. So it's in between here. And that's just going to give us the right side. But in fact, the test that we're conducting is a test of difference. We're going to check if it's higher or lower. And when we say or, we have to add the probabilities from both of them. It's the same value that we're adding on the right and the left. So we can just double the value that we get here. So our value, the best we can do is find that 1.878 is right in here. And that means that the right tail is between 2.5% and 5%. So if I use this as my value, I say this is 1.878, then this area is between 2.5% and 5%. It's not precise because we need more decimal places to be exact. And Excel can do that. But the table is just giving you a rough idea. Okay. Okay, so what? So what are we doing? So what we're doing is the next step is the P step, the P value. So we're going to do the P step, and the P value, remember, is the probability of being as extreme or more extreme of, sorry, I'll write it like I did last time. Probability of seeing, in this case, I'm going to just say test statistic in general, as extreme or more extreme as we saw, given H naught is true. So what does that look like? So I just teach you to draw it. And we draw, what do we draw? We draw our test statistic on it. So this is a T29 table or chart or graph or distribution. And the T-stat that we got was 1.878. I'm going to check what's the chance of it being greater here. But I'm also going to check on the other side because it can be higher or lower than that. So the chance of being over here, I said, because on the right-tailed table, so the T distribution will give you the right side. The Z distribution gives you the left side, right? And need to remember that. So this is between 2.5% and 5%. And also this is between 2.5% and 5%. And so that means that the chance of seeing it so much higher or so much lower, and the reason why I do that is because going back, that the P step depends on what you put here. So otherwise we don't use the alternative hypothesis until we get the P values. That says check on both sides. So the answer is that the P value is equal to double. So the P value is equal to double. So it's going to be 5% to 10%. Double. So now, what is the conclusion? It means that the result that I got, 162, is different or not different from 150. What do you say? They did this trick to us. They changed the significance level. What does that do? So that changes how I'm going to do my concluding step, the last step. Oh, I don't think I called it the concluding step in the last problem. Oh, I did. I don't remember doing it, but okay. So the concluding step is always, no matter if it's a left-tailed, two-tailed test, Z or T, the p-value is always to check p-value less than alpha, reject. In this case, alpha is 1%, but our p-value is going to be between 5% and 10%. Is not less than 1%. So we say we fail to reject. 162 is not different from 150. We didn't see anything surprising. The test is not significant. We didn't find anything significant to report. So what are the options here? Fail to reject since P is between 5 and 10%. Right there. T. Questions for me? If I lost you, where did I lose you? So I recommend for the p-value, just draw it. And remember, it relates back to the alternative. So we've used number 5. We use number 6. I use the method of the HAPC, the 5 steps. And I did a right-tailed test and a two-tailed test. What do you guys want to see next? I'm going to check the homework question that I was asked to check. What do you want to see me do next? 41 and 46 inference. Let's read some statistical output. How about that? Okay, let's look at 41 and 46, and then we'll look at some output. Okay, 41. Let me see who asked the question. Maybe they figured it out now. I'm not sure. It was Paola. Have you sorted out the problem here, Paola? Let's do this 41. Confidence interval. What should we use? We have a sample of 25. And we have the mean and standard deviation. First question, is this about a mean? Are we doing inference on a mean? It's okay, Adaira. She tells us that she has a connection issue. It's okay. So is this problem 41 about a mean or about a proportion? So it tells you here, this is how it tells you. It tells you right here, mu. The confidence interval for the mu. So that's the mean. That's where it tells you. Okay. And the next question is, because it's about the mean, do we have sigma or do we not have sigma? In other words, do we use 5 or do we use 6? Do we have sigma or do we not have sigma? Do we have the population standard deviation or not? Okay, we do not have sigma. There's no information on sigma. All we have are the results from a sample. So these are the sample mean and standard deviation. All right, so then we have to use number 5. So we use number 6 because we don't have it. We have to use this formula here. The mean plus or minus T star. And what do you get? Here's the mean, 180, 1980. So they're all the same. And so then you have to take T for 99% confidence interval and what degrees of freedom? Right, Adriana is right on track. We need the T value for a 99% confidence interval with degrees of freedom equals 24. So how do we do that? Okay, so we need to go to our T table. We go to 24. We're going to use this row here, and we want it for the 99% confidence interval. So we use so I recommend just go below for the confidence interval. It can get confusing. You go from the top to do this. Um, just to avoid that, go like this. So this is going to be the critical value. So you need to be 2.797 standard deviations from the mean to have 99% in the middle. So 2.7, yeah. This is the critical value for 99% confidence. This is the critical value. So then you take that and you multiply that by S over root N. So you're going to take 180, 1980 plus or minus, let me write the formula. X bar plus or minus T star S over root N. So T is 2.797. So 2.797 standard deviations away. S was given as 30. No, not 30. What was S? I gotta go out. S was given as 150. Divided by the square root of, how many were they? 25. So you're dividing 150 by 5, which is 30. So this is how you get it. And so that's your margin of error, your M. $83.91, so it's C. All right. Okay. So that's okay. I guess maybe she didn't know about using, or wasn't clear about whether you use 5 or 6. Okay, let's look at 46 now. Problem 46. Here are the degree of reading power summary scores for a sample of 38 third graders. These students can be considered to be a simple random sample of the third graders in a suburban school district. DRP scores are approximately normal. Suppose that the standard deviation of scores in this school district is unknown. A 95% confidence interval for mean score based on the summary statistics are what? Okay, so are we going to use 4, 5, or 6? Is this a question about the mean? Right. It says right here, mean score. Okay. That's the result you want for mean score. And the standard deviation, sorry. Do we know the population standard deviation or not? We do not. We do not. It tells you explicitly, it's unknown. Okay. So you have to use number 6. You have to go to the T table. You have to look for the critical value for 95% confidence, which is 1.96. So it's either A or B. It's either A or B. No, that's for Z. So see, I just messed up. For the T distribution, you have to check. This is a trick. So this is for the Z distribution, this 1.96. But what about the T? I don't know all of those. I have to go check it on the T table for 95% and degrees of freedom are, so as soon as I go on the T table, it's 38 is the sample size. So I have to go to 37. What do I do when I go to 37? There is no 37. What do I do? I do not interpolate, but I have to pick one. And I believe in the notes, I said something about that. What do I say about it? When it's not. It's going to be go to the higher one, but I'm pretty sure I tell you here. Mhm. Much higher. See if I find. No. I think the rule is, so we have some rules, right? That I outline. I teach you the T table here. Okay, the rule is use the T value that's closest. If it's not on the table, use the one that's closest. Okay, you don't, so in this case, it was 27 degrees of freedom. So it goes to the closest one is to go up. It's not, I guess it's kind of like rounding. Yeah. If you use Excel, you get the exact value. Um, on these exercises in the notes, I don't use Excel. So if you use Excel, you might get confused. You got to use the table, but in real life, use Excel or use something that's more exact, of course. All right. So on the T table, the one to use is going to be, just to clarify. So we're going to go up 95 to 27, but then 37, not 27. It was 37 that we needed because we had 38, and 37 is not here. But this is the closest. 2.021 is closer because 40 is closer to 37 than 30 is. So that's why it's 2.021. Okay. So you start on the bottom with the confidence level and go up. So in that place in the notes, I go through the rules that I set. So you get the same answers as me. People could debate about which way you go, but this will get you the same answers as I have in the notes. Okay, so 2.021, and then you have to take S, which was calculated in the output, 6.547, divided by the square root of 38. Aha, you see how they trick you? Be careful. The n minus 1 is just used for the degrees of freedom. Don't take the square root of n minus 1. People who aren't confident might pick the wrong one, okay? So D is the answer. Okay, so you should be able to do it in Excel. You should be able to do it with the table. So I've answered those two questions, Paula. It's all good, right? So it's just doing the steps that I taught you. Is it about the mean? Is it about the proportion? And then if it's about the mean, do you know sigma? That's it. And then you know which formula to pick. What was I just thinking about? The last thing I wanted to do. The tables, output, statistical output. It's kind of like statistical output here. Okay, so number 52, here's some computer output. What does the computer output tell us? We don't have any other information. We just have the output of a z-test. So what do we know looking at this? We know that they're testing the mean to see if it was equal to 64 against it's not equal to 64. Of the sample, they got 62.697 as the mean in the sample. And the z-statistic was assuming that it was 64. They standardized 62. So they assessed the evidence. 62.697 was assessed minus the mean of this one divided by the standard deviation. And they got this. So what's the p-value? So you don't have to do anything except compute the p-value for a two-sided test. So make sure you answer the questions. You don't do more than you have to do, because I taught the 5 steps, but you should be able to answer just parts of those kinds of questions, or steps themselves. So for this problem, you just draw onto the I'll project in a second. I'm just copying. So I draw the Z, so I put the Z there to remind myself. When you have T's, you should remind yourself drawing the T. and the degrees of freedom as well. And I'm going to put, because it's a two-sided test, I have to put down negative 1.955 and positive 1.955. And I check what's the chance of being beyond that, the extremes. And then that's it. And it's not 0.955. You can check that in Excel or just round this for the table's sake. Just round it. Oops. And we know at negative 1.96 and positive 1.96, the p-value is going to be 2.5 on this side and 2.5 on this side. So it's 5%. Yeah, if you go into Excel, you're going to be more precise. Adriana got 0.0504. Right. Okay. So you guys seem good, or the people who are responding seem to understand. The rest of you, you need to catch up. And everything is there for you. If you have any questions, I mean, I can't teach you anything while you're writing the test, but I'm going to post the test at 6. If you have anything you want to clear up with me, you can contact me. Is there anything else? You can contact me anytime, and I might not answer the question, but before 6 o'clock, if you have anything you want me to clarify that's serious, you can let me know. You can tell me now, and I can look at it. But I do think you have everything you need to succeed on this test. You have the distribution of the exam, where to focus, inference, is the heavier chapter. That's why I spent time today. So any other questions for me before we go? No? All right. Okay, so I just want to say,
Professor,
uh-huh.
Professor, sorry, can you repeat the due date for the exam?
It's gonna be Wednesday because I'm giving you the test a little bit late, so I'm giving you some extra time. We have some extra time. Oh, I said Tuesday, but Wednesday the 13th, um, at midnight.
Thanks.
Yeah, so I'm gonna post it at 6. Sometimes it doesn't help people because they're busy in the week, but I'll just try and work hard this weekend. Pull time to yourself away so you can focus, get this done, and then just maybe correct it or work on minor things during the week before you submit it. But you shouldn't have to take too long with it unless, you're still studying.
Do you know how many exercises you're going to be in
I have
exam?
provided the distribution on the platform and it tells you
Yes.
exactly.
Okay.
It tells you
Thanks.
exactly here. Distribution. It tells you exactly what you to expect. If you didn't see it, I'll show it here. No surprises. So this is from the link called Distribución Aproximada del Examen Final. And there you go. 16 multiple choice questions, 5 out of 7 short answer, and then one problem that comes from module 6 and 7, pages 42 to 48. And that's it. And this is the emphasis for the exam here. Okay, well, thank you so much. It was a pleasure. These groups are getting better and better, so you guys are the best so far. I'm very pleased with the feedback I'm getting, and I wish you guys the best in this course and in the program and in your future endeavors. Keep in touch. You can join me on LinkedIn. We can keep in touch. A lot of students do add me. Well, I'm gonna say a lot, but some do. And so over the years, it's added up. Okay, so keep in touch the next few days. If you have any questions, let me know. I will post the grades so you can see that. And then I will post the final grades by Monday. So if you have any disputes, check them on the weekend. I hope to have the grades up by Saturday so you can check next weekend. If there's any issues that you have, you can meet with me.